So we have looked at the theory of mass balance modeling and how to set up and solve single box as well as multi-box models. In this lecture, we will have a couple of examples to give us a little bit more practice. So the first example, we consider a pollutant emitted in a room at emissions E milligrams per day, and the pollutant has a constant decay of K 0.5 per day. So this is our rate constant for loss. There is generally no ventilation. Only every 2 days the windows and doors are opened for a few minutes and the entire room is flushed instantaneously, which means from between 0 to 2 the mass builds up, and at time 2 days immediately everything is flushed out. So sort of the mass goes away, and then the no ventilation condition is immediately established for the next 2 days and so on. Consider mass at time 0 to be 0. Plot the evolution of mass in room with time. What is the maximum mass possible in the room? What will be the time average mass in between the ventilation periods? Okay, so we will do step by step. So this is our room with emission E starting at time 0 and the loss reaction R. So we will set up our dm by dt equation for the room. Dm by dt equal to E minus R or E minus K R times M, or here we have used the term K, so we will just simplify it. So we have E minus K M. Okay, now we know the solution to this equation we have done several times, so or we have looked at several times. MT is M 0 e to power minus kt plus E by K 1 minus e to power minus kt. Okay, so we know now consider mass at time 0 to be 0. So M 0 is equal to 0. So our solution is M at T is equal to E by K 1 minus e to power minus kt. Okay, so this is our solution. Now we are ready to do the first problem. We have plot the evolution of mass in the room with time. So we know that the pollution accumulates until 2 days. So I am just going to rewrite. I will put the values of K. So K is 0.5. So 1 by K is equal to 2. So 2E 1 minus e to the power T by 2. So we have 2e 1 minus e to power T by 2. So from time 0 to time T, time 2 days there is accumulation, and at time 2 days we reach a mass M at 2, which will be 2e 1 minus e to power minus 2 by 2. So this is 2e this is 2e 1 minus 1 by e, which is equal to 1 minus 1 by E. So this is total equal to 1.26, approximately 1.26 E. So since the flushing happens and the concentration becomes 0, the profile will look as follows. Start at time 0, then time 2, 4, T in days, and we have M at T here. So now let us see how the mass will evolve over time. So one thing is that the evolution is exponential, and we will reach until 2 days. So there will be some increase until 2 days, and the mass will reach 1.26 E, 1.26 E, and then there is instantaneous flushing. The room is flushed instantaneously. So mass will again drop to 0. Then the same process will start again. So again the mass will increase to 1.26 E, and then again go down, and so on. So this is the evolution of mass in room in time. Now what is the maximum mass possible in the room? So here again, okay, mass is 0 times 0. So maximum mass possible is actually 1.26 E given the conditions, because the room cannot accumulate more because there is flushing happening. Now what is the time averaged mass? Okay, so for time averaged mass we have to write our original equation. And what is time average mass for the 2-day period? So we are going to derive time average mass for the 2-day period, and the way it will we've done is the time average mass for time 0 to 2 or 2 to 4 is actually 0 to 2 is integral 0 to 2 mt dt divided by integral 0 to 2 dt. So here we have to integrate the mass equation. So this equation we have to integrate. T equal to 0, T equal to 2. So the integral is integral of, so E by K remains constant. I'll just do this again. E by K integral of, so again 0 to 2 1 minus e to the power minus kt dt. So now what will this be? E by k, the first term will be dt, so it will be t minus 0, or actually the so it will be, first term will be I'll just write like this, t 0 to 2 minus integral is minus 1 by k e to power minus kt. Here we have again 0 to 2. So this is solution is e by k 2 minus 0 plus 2 e to the power minus t is 2 and k is 0.5, so 0.5 multiplied by 2 minus plus 2 e to the power 0, because here 0.5 is k multiplied by 0. So e to the power 0 becomes 1, and this is 2 divided by e and plus 2. So this term becomes e by k is basically 2 times e. This is minus sign again, sorry. Minus. So 2 by e plus 2 into 0.36 minus 2. So this is 2e multiplied by 0.72. So now the time averaged mass will be 2e multiplied by I will write the whole algebra first. So this will be 2. So this will be 2e 0.72 divided by 2 minus 0. So this is 2. So 2 and 2 will cancel out, and we will have m bar is equal to 0.72e. So this will be our time average mass. So that's the first example. Now a second example. We have a house with 2 rooms. R1, room 1 and room 2. There is only one inlet of air into the house at R1. So this is our air inlet. Air enters at 10 meter cube per hour and contains a moderately harmful gas at concentrations 5 milligrams per meter cube. Okay. Now within the room 1, X is also produced due to cooking fuel burning at a rate 25 milligrams per hour. R2 is a baby room with no source of X. The only circulation of air in R2 occurs via entry from R1. So this arrow, and exit via window in R2. So air goes to R1 from here, R1 to R2 here, and then goes out of the window. The question is, calculate the steady state concentration of X in R1 and R2 and what is the residence time for X in R1 and R2. Okay. Then if it is decided that the house will change its fuel and there will be no more in-house source of 25 milligram per hour, what will be the steady state concentrations of X in R1 and R2? And then the second is, instead of stopping the source, it is decided that the room R2 will have another ventilation, another window, so that air can enter 10 meter cube per hour. So the same air, but we have a more flow rate. What would be the new steady state concentration of X in R2? The in-house source will continue as it is. So then this we can compare which intervention is better, remove the in-house source or make a new window to allow more flushing. We will go one by one. First is calculate the steady state concentrations of X in R1 and R2. So what are the sources and inflows and outflows? We have R1, R2, we have F in, only single F in is there. So I can just use one, and we have the same F out happening, or well, some F out but same airflow, and we have F1, 2. The concentration is C1, mass is M1 in room 1, concentration is C2, and mass is M2 in room 2. There is a emission in E1. There is no emission in room 2. Okay. Now F in is the mass of chemical coming in. So this is equal to airflow, which is 10 meter cube per hour, multiplied by the concentration of the incoming air, which is 5 milligrams per meter cube. So this is equal to 50 milligrams per hour. E1 is 25 milligrams per hour. Okay. M1 can be written as V1 C1, and V1 is basically equal to, if we see the room dimensions, V1 is equal to 3 multiplied by 5 multiplied by 5. So V1 is 3 multiplied by 5 multiplied by 5. So mass is C1. So this is equal to 75 C1. Oh, sorry, 75 C in. Oh, excuse me, 75 C1 only. C1. Yeah. Then E1 is there, outflow is F12. So now F12 would be equal to the concentration in 1 C1 multiplied by the airflow 10 meter cube per hour here. So this would be C1 multiplied by 10 equal to 10 C1 milligrams per hour. So now we are in a situation to write the mass balance for the room 1. So dm1 by dt equal to F in plus E1 minus F12 actually. So this is equal to 50 plus 25 minus 10 C1. Okay. Now what is with the second room? This 10 C1 F12 goes to room 2. So dm2 by dt is equal to F12 minus F out. Okay, so F out is C2, concentration in room 2, multiplied by 10 meter cube per hour, which is the airflow going to the through the house. So this is again equal to 10 C2. So dm2 by dt will be 10 C1 minus 10 C2. So we have actually quickly arrived at the mass balance equations for C1 and C2, or M1 and M2 actually, for the two rooms. Now at steady state, we have been given the steady state condition. So at steady state, both of them, dm1 by d2 and dm2 by dt is also, dm1 by dt and dm2 by dt are 0. So 10 C1 minus 10 C2 equal to 0 will imply C1 is equal to C2 at steady state. And this dm1 by dt equal to 0 will imply 50 plus 25 minus 10 C1 is equal to 0, which implies 10 C1 is equal to 75, or C1 is equal to 7.5 milligrams per meter cube. So C1 is 75 milligrams, 7.5 milligrams per meter cube. So that's one part done. So I'm going to write both these down. C1 equal to 7.5 milligram per meter cube, and C2 is also equal to C1 equal to 7.5 milligrams per meter cube. So that's the steady state concentrations over. Now what is the residence time of X in R1 and R2? Okay. So residence time in R1, so tau 1 will be M1 by loss, so F12 at steady state. So M1 will be 7.5, or I'll write the algebra first. This will be C1 V1 C1 V1, and F12 is C1 multiplied by the flow rate, to 10. So actually tau 1 comes to be V1 by 10. So tau 1 is equal to the volume of the room, 3 into 5 into 5 divided by 10. This is meter cube, and this is meter cube per hour. So tau 1 is equal to 75 by 10, or tau 1 is equal to 7.5 hours. Okay. Now similarly what will be tau 2? So tau 1 we have 7.5 hours, because tau 1 is mass divided by outflow. So C1 V1 divided by C1 multiplied by the outflow 10. So V1 by 10, volume 75 meter cube by 10 meter cube per hour, 7.5 hours. Tau 2 similarly would be M2 divided by F out. Tau 2 would be M2 by F out. So here M2 is C2 multiplied by volume into divided by F out. So C2 multiplied by 10 meter cube per hour, this thing again. So what is the volume? So this actually becomes V2 by 10. V2 is 3 into 4 into 5. So 60. This is 60 meter cube by 10 meter cube per hour. So tau 2 is 6 hours. So we have solved this. Now the second is that so we have done with tau 1 and tau 2. The next scenario is that there is no in-house source. So next no in-house source. So what will be the steady state equation? So no more in-house source. So E1 equal to 0. So in this case we only have flushing in and flushing out going on. So dm1 by dt is equal to f in minus f12 and dm2 dt is equal to f12 minus f out. So I will write this. F in is basically 50 milligrams per hour and F12 is 10 times C1 and this is basically 10 times C1 minus 10 times C2. At steady state both are equal to 0. So this implies C1 is equal to 5 C1 equal to 5 milligram per meter cube and C2 also is equal to 5 milligram per meter cube. So in-house source has reduced by the concentrations from 7.5 to 5 meter cube. Now the next is, instead of getting rid of the source, room will have another window, so air can enter 10 meter cube per hour. So our dm1 by dt equation, which was f in, here the changes are only happening in room 2. So dm1 by dt equation remains unchanged. So steady state we will have the same C1. This will be equal to, as we have derived in this one, 7.5, because there is no change in that equation. We will have 50 plus 25 minus 10 C1 equal to 0. So C1 again will be 7.5 mg per meter cube. So in terms of C1, no change. But dm2, let us see. Now we have an extra term coming in dm2. So we had f 1 2, but now we also have a new F in 10 meter cube per hour. 10 meter cube per hour multiplied by the concentration, and recall the concentration of outdoor air is 5 milligrams per meter cube. So we have 5 mg per meter cube. So we have this much extra mass coming in, and outflow is 10 plus 10 now, because we have 20 meter cube of air coming in times C2. Because now if this is room 2, we have F12 coming in, plus we have another F in, which is 10 times 5, and then we have 2 times 10 meter cube per hour going out. So 10 plus 10 multiplied by C2. So we have F12, which is basically 10 times C1, then this is 50 minus 20 C2. 10 times C1 is 75. This is equal to 0. So 10 times C1 is 10 into 7.5 plus 50 minus 20 C2 equal to 0. I'll just rewrite this. Equal to 0. So we have (75) plus 50 equal to 20 C2, or C2 is equal to 125 by 20. So 125 by 20 becomes 6.25 mg per meter cube. This is actually greater than 5, which was when we had just stopped the source. So in terms of C2, actually stopping the in-house source was better, because then no pollutant air was less polluted air was coming in, rather than this scenario in which we have added flushing but the source has continued. So which intervention is better, for C1 or room 1? No effect, because there will be, for C1 we have actually no effect compared to the original situation, but if you decrease the emissions, then stopping the source is better. because the concentration was 5 and which is less than 7.5. Okay, now in C2 the concentration is 6.25, so 5 is again less than 6.25. So here also stopping source is better rather than adding more flushing. So in both the cases we find that it is better to stop the source rather than add more flushing in one of the rooms. Maybe we can have scenario when we have both the rooms being flushed, or someone installed filters at the room so that the incoming air becomes 0 concentration. So but so now you can see using the multi boxes and simple mass balance approaches we can already solve several types of scenario based questions. So in summary, in this week we have covered the concepts of mass balance, resistance times, steady state. This is steady state. Steady state. And we have also now done some examples, utilizing these concepts to get a sense of like time average concentrations, or checking the scenarios of what is useful or what is better than the other. All these now things will be useful when understanding the rates of different processes and applications and their implications indoor air quality for whatever the lectures which are going to follow.